Can you guys see my PowerPoint on a periodic table right now? Do you see a periodic table? Can you see my PowerPoint slides? What do you see on your screen?
I can see.
Okay. Do you see a electron filling and orbitals?
Yes.
Okay. I want to make sure that you can see. All right. I'm going to go to the, hold on a second. Okay. I think I covered some of the periodic properties, melting point and boiling point for halogens and the alkali metal and the noble gases last time. Those are the ones we covered. So today we're going to look at the more details of electron configuration. What do you mean by electronic configuration is, the meaning of electron configuration is, you write down the atomic symbol and show arrangement of electrons with symbol, some kind of notation outside the nuclear space, extra nuclear space. Electrons are more like waves. They are small particles. They behave more like waves. When something behaves like waves, it's more like energy. They have wave shapes. The energy is quantized. So therefore, proper description of electron distribution around the nucleus is describe their wave shapes. So different energy levels have different wave shapes. So these energy levels have increasing energy. Some of them have lowest energy, some of them have increasing energy, one after the other. Lowest energy level for electron is called the ground state electron. So we're going to look into this and have you understand the electronic configuration. All right. So we have to look at electron as a wave shape. So wave shapes, I'm going to show in the next slide. There are four, first two here. There's one here. Can you see my first one? I circle it. Can you see red?
Yes.
Okay. I want to make sure that you see that. I can write on it. Okay. Now the second one is similar shape, but it has 1s for the first one, second one is 2s. The only difference is they are both shapes are similar. We call S shape of an electron. First one is found at the lower level energy. One is shell number or period number. We're going to talk about this in a minute. Second, 2s is the second one here. I'm going to circle, square it here. Is 2s. It belongs to the second period or the second shell. It's bigger. So you can have s orbitals, s wave shape like that for electron in different energy levels. They become bigger, higher the energy. We're going to talk about it. What is the first shape we talk about here? Is a S shape. S shape is spherical. Now the electron can have a P shape. There are P here. I'm circling. Shapes are called orbitals. Wave shapes of electron is called an orbital. But this P shape has three wave shapes. First one is along the px axis right here, px. Along this one, py. Along this axis, pc. So there are three p orbitals. We call them px, py, pc. What you are learning from here is this. Electrons in an atom around the nucleus takes up different wave shapes. So one of the shapes is S shapes, spherical shape. Other one is P shape. P shape has three p orbitals. There are all put in one diagram right here. This is one of them. This is one of them. That's three of them are here, put in all together. So this is the description of the, okay. This is the total picture of wave shapes. The first one is a S. We talked about it. Second wave shape is there are three p orbitals, px, py, pc. You see that three shapes in here. The third shape is d orbitals. There are five of them. Do you see five altogether here? 1, 2, 3, 4, 5. The other shape is F shape. There are 7 of them. If you look at number of wave shapes, S has is 1. Number of wave shapes, P has is 3. Number of wave shape, D has is 5. F shapes are 7 of them. Now you have to kind of get this idea. Electrons in an atom are present in one of these shapes. An electron in one of these shapes. When you put electron into, they go to one of these. So which one they go, I'm going to show you, okay, for each atom of an element. So how many of you know how many wave shapes electron can take up in extra nuclear space? How many shapes? Types of shapes. Do you see 4 shapes here? S, P, D, F. All right. Okay. Next idea is electron also have a spin. Like a planet can spin opposite way or clockwise or anti-clockwise. So in a orbital like this, SPDF, there are the number of electrons with the opposite spin is clockwise, anti-clockwise is shown like that. There are 2 electrons that can go into one of these S shapes with opposite spin. There are 6 of them. 3 times 2 is equal to 6. 1 times 2 is equal to 2. This gives 5 times equal to 2 is 10. Then 14 here. 14, 10, 6 total electrons can go into one of these 2 atomic orbitals. Therefore, shapes gives SPDF shapes for electrons. Spin gives each atomic orbital 2 electrons. When they go into an atomic orbital, they normally found as a paired electrons. Paired electrons means when this one is this way, this one is that way. In the atomic orbital, it's found in as a paired electron pair. Now let's look at this. How we get the electronic configuration for hydrogen. If you look at hydrogen, is here. Do you see that I circled the hydrogen? This is the periodic table that we described. This is the periodic table normally found in the world. Hydrogen is here. Atomic number of the hydrogen is 1. There's one electron in the hydrogen. There's 1 electron. Where does that 1 electron go to hydrogen? If I write down here, hydrogen, this is the same idea here. On the left side, show different shapes. That electron, when you add an electron to hydrogen, it goes to 1s. So electronic configuration for hydrogen is 1s1. I cannot write. Hydrogen is 1s1. How do I get that one? I go to the periodic table. This orange area is S shapes of atomic orbital. Electron have S shape. This is P shape here. This is D shape here. This is F shape here. Do you see that different areas have different, when an electron goes to them, one of these areas, it take that shape. So do you see how I get hydrogen is 1s1? What is helium? Helium has 2 electrons. Why I say 2 electrons? Atomic number is 2 here. Right here, helium. Helium is on that corner. 2. Therefore, you go put 1 in there and go to here. That's where helium is. 1s2. You see that? We're going to explain this in slides, in next few slides more. What is the idea I'm trying to get you to understand is, periodic table is structure, is basically structure of the atom, electronic structure of the atom. So it shows where the S areas are. First 2 group has S shape. The next groups here in the middle, which are colored, yellow, is D area. Now these 6 groups here are P shapes. Now the bottom part, these lanthanide and actinide, when an electron goes into them, is F shape, acquire X shape. So all you have to do is fill in the electrons to different shapes, starting from that idea. For example, if you want to find the carbon, right here, carbon is right here, right here. You start from 1s, 1s2, 2s2. There are 2 places, 2s2, 2p2. Carbon is that. Carbon is 1s2, 2s2, 2p2. I am showing how to get simply. All you have to do is use the periodic table and get the electronic configuration. Do you have any questions so far?
No, sir.
Okay, let's move on. You can ask more questions later. If you look at the periodic table, I described there are periodic table. Periodic table is showing electron shapes for different blocks or squares in the periodic table. The first 2 columns are S shapes that this is D shapes, the blue one D shape, the yellow ones are F shapes, the P's are right here, that 6 of them. Now, I talked to you about that. S can have maximum of 2 electrons. S orbital can have pair of electrons, paired electrons. P orbitals can have 6 electrons. D orbital can have 5 orbitals, we shown paired up here. F orbital have 7. So they're counting that 2 electrons, maximum number of 2 electrons in S orbital, S shape. Orbital is a S shape. So this is represented by long form of periodic table. In the periodic table, lanthanides and actinides were taken out after this place and put in on the bottom. You remember that lanthanides and actinides are at the bottom. So basically periodic table gives the shapes. Okay, let's do a problem. Now, before I go about it, there are 7 periods in the periodic table. These 7 are numbered 1, 2 through 7. This period is also called shell number. Shell, S-H-E-L, shell number. Shell number is equal to 1 here. Shell, second shell, third shell, fourth shell, number 4, 5, 7. So the shell where the electrons are filled up successively. First it goes here, then goes down there, then move back here, periodic nature. Then you fill it, move back here. So you go on a journey here, from here to here, until you find the element, wherever the element. For example, elements is right here. So you count the number of electrons and keep filling it until you reach that point. Okay, the electronic configuration is obtained by looking at different electronic shape or atomic orbitals in the periodic table. The maximum number of a first shell is, there's only one S, is 2. S can hold only 2. P orbital is 6. Second shell has S and P orbitals. So therefore it is 8 total. 2 plus 6 is 8. Third shell, if you go back, 3S, 3P, 3D, that's 18. 2 times 2 times 2 times 6 times 10. Let me show you that part. That's where the 2, there, 8, there, 18, because the 3D third shell has 3S, 3P, 3D. So 18 of them. So you can see in each period how many orbitals are there. Therefore, number of electrons in that shell is given. You can obtain also this using a formula. This is called N2 squared. N is the shell number. For example, shell number here is 1 squared. 2 times 1 squared is 2. N is 2 here. 2 times 8. 2 times 2 squared, 8. N is equal to 3, you get 18. N is equal to 4, you get these numbers. All right? So this is basic idea. Now, if you look at the periodic table, this is lithium electronic configuration right here. How do I get that? Lithium is right here. There are 3 electrons in lithium. So we have to fill in 3 electrons. You start with first one here, second one here, that's up to here. Then the third one goes to that one. Therefore, electronic configuration is 1s2, 2s1. For beryllium, it has one more. We have done second row. Beryllium has one more electron, therefore it's going into 2s also. Beryllium is right here. So boron is right there. Boron has 5 electrons. First 2 goes to there. 2 goes there, 1 goes there. So boron is 1, 2, 3, 4. 1, 2, 3, 4, 5 electrons. If you look at boron, there's 5 electrons, 2 plus 1. So last one goes to p orbital right here. Do you see this, what I'm doing? For example, how do you get the carbon? Carbon atomic number is 6. 6 is the same number as number of electrons. Proton number is equal to electron. So you had to fill 6 electrons to carbon. You start with here 6. 1, 2, 3, 4, 5, 6. That's where the carbon is here. Carbon is right here. So carbon electron configuration. Therefore, nitrogen is 1 more electron. How many of you now understand if I ask you what is the electronic configuration of carbon, how do you get that? You go to the periodic table, put 1 electron in 1s area. 1s area is, the first area is 1s. This is helium. Here, helium is placed under noble gases. So second electron, 1s2, 2s2, 2p2. There are 2 electrons here. All right. Do you have any question about how to get the electronic configuration of simple atoms? We only ask you about question about this area. This area. We are not asking everything in the periodic table. Okay. So there's also what we call it noble gas format of electron configuration. For example, potassium, right here. Potassium is right there, right here. So when you do potassium, you do 1s2, 2s2, 1s2, you move from here to here, move from here to there, and move from here to there, and end up with right here. Okay? So those are the number of electrons you need to fill. The last shell that you fill is 4s1. Last shell is 4s1. Now, because electrons in the outermost shell, which we call valence shell, I'm going to define it in a minute, is very important for chemistry because that's where the electrons make bonds. So rest is kind of inside the atom. Therefore, we shorten, abbreviate this to argon right here. Argon is before right here. This is argon. Helium, neon, argon. So we put the argon as the core. Argon with the square bracket. You see that? Therefore, electronic configuration could be written for the full electronic configuration or make it shorter by putting parentheses and finding out going backwards and finding out the noble gas elements before potassium. Before potassium was argon. Before lithium, it was neon. So it depends on where the element is found in the periodic table. Do you understand that now? Electronic configuration is written in terms of electronic shape around the atom. So we have to write down using the periodic table 1s2, 2s2 arrangement, and we can abbreviate using the co-format and use that in describing properties of chemical properties. Chemical properties are described by electronic configuration. All right. There's also another form. Okay, let me go back there. There's at the bottom, I couldn't see my menu covers that. In the bottom of the periodic table. Let me go back to the next one. The filling order, can you see something in the bottom here? Somewhere here. 1s2, 2s2, 2p6. Can you see that? There's a filling order is at the bottom. This filling order is shown up here. I can see the filling order. Is the following the sequence in the periodic table as we described: 1s2, 2s2, 2p, 3s, 3p, 4s, 3d. If you move through the periodic table, this is the energy wise. This is the ground state, lowest energy. First electron goes there. First 2 electrons goes in there. Second, third, fourth. 6 goes there. 2 more goes there. Now you can also obtain using this diagram, electronic configuration. But it's same as using the periodic table. So therefore, just get the idea. Electrons in the lower shell numbers which have lower number is low energy. Lower the shell number, lower the energy of the electronic atomic orbitals of the. Therefore, 1s is lower energy than 2s. 2s is lower energy than 2p, so on. The filling order is describing that. So now let's summarize this. How to get electronic configuration. Orbitals in the order of increasing energy from lowest to highest are used. For elements in the periodic table, the order is, this is visually we went through that order. Start from 1s area, then goes to 2s area, and 2p area, 3s area, 3p area. That's a filling order of electrons. So if an electron goes to one orbital, it can have 2 electrons with paired up spins. Paired up means one spin is clockwise, other one is anti-clockwise. But you have to understand, p orbitals have 3 wave shapes: px, p, py, pc. Therefore, 6 electrons can go into p orbitals. So p orbitals, when you're filling p orbitals, there's total of 6 electrons. 10 electrons. There's only total of 2 electrons, 2 electrons, 6 electrons, 2 electrons, 2 electron for S. P is 6, S is 2, D is 10, P is 6, S is 2, 14, 4. There are 7 wave shapes for D electrons. 10, 6, 2, 14, 10. So that's the maximum number of electrons you can have. Okay, these have more than one orbital. There are 3 orbitals here. D have 5 orbitals. 5 here. P has 3. P has 3. 4 has 7. D has 5. 6 has 3. 7. 5. So total number of electrons in 5d orbitals, 2 each, become 10. This number multiplied by 10, that's the maximum number of electrons. So when you have electronic shapes having more than one atomic orbital, like P has 3, D has 10, F has 7. So you have to increase the number of electrons by multiplying 3 times 2, 6 in P level. Now rule 3, when there's a set of orbitals with equal energy, that means when you have D, F orbitals, there are 3, 5, 7. You have to follow this rule. Orbital becomes half filled before any of them become completely filled. For example, if you have P3, there are 3 atomic orbitals in P3. You fill them up separately, parallel space. So you cannot fill them up until you fill all of them completely full. So if it is F orbital or D orbital, same follows. You have to, when you're filling P orbitals, first D orbitals, first 5 electrons should be put in parallel. Then you start it. If it is P6 here, then you start filling other 3, other 6. So until all of them are paired. For example, this is the electronic configuration of carbon. This is the electronic configuration we obtained from periodic table. You have to expand the P area right here. This is 1s, 1s2, 2s2. Now this is 2p2. When you're filling 2p2, you have to put 1 in each before you put in the third one, anything. All right. Therefore, there are 2 unpaired electrons in the carbon atom electronic configuration. They have unpaired electrons have magnetic properties. Therefore, they affect the properties of the atom if they are unpaired electrons. So, do you get the idea about electron configuration now? What is electronic configuration in noble gas notation? We already abbreviated the co-electrons for potassium. Remember in the previous slide, we did that. The same is followed for fluorine. Fluorine, noble gas before fluorine is helium. Before going to fluorine, helium is the noble gas. You started the filling up from helium, then 2s2, 2p6. Now, but you have to count the number of electrons, right? Remember, fluorine doesn't have nine electrons. There's only 7 here. Where's the other 9? This is 1s2. So therefore, you have to keep still, there are a total of 9 now. Fluorine electronic atomic number is 9 electrons. So anyway, after you get the full electronic configuration, you can abbreviate that. So for example, this is the fluorine total electronic configuration. My pen stopped writing. That's okay. Now, if you look at this, the p orbitals here, two p orbitals. Two p, there are 5 of them. When you're filling them up, you put 1 in each on the box diagram at the end. Then put the second and the 4th and the 5th in the next 2 boxes for p orbitals. Therefore, if I ask you, how many unpaired electrons are in the fluorine atom? Unpaired means that single arrow on the last box here, right here. Now it starts working. That's good. We're talking about here. So it's very important to show how many electrons are in the valence shell. Valence shell is second shell here, where we made it shorter. Valence shell is second shell. Valence shell is the highest period number, atomic orbitals with highest period number. It's 2 for fluorine. Now we use box diagrams for electronic configuration. Box also represent like 1s, 2p, 1s or p orbitals or d orbitals. Box represent orbitals. For p orbitals, there are 3 boxes. S orbital, there's 1 box. For d orbitals, there are 5 boxes. For f orbital, there are 7 boxes. An arrow in these boxes represent an electron. See this arrow here. A pair of arrows with head opposite direction represent the paired up electron pair of electrons. You cannot put atoms in a box, electrons in a box with parallel spin. They are unstable. When you put in a box 2 electrons, it has to be paired electrons. If you have 1 electron in an orbital, it is an unpaired electron. There's no second electron pair. For example, this is again carbon. Now we normally abbreviate, only look at this part. This is the helium. So anyway, we can write down electronic configuration in any format. It could be in box format, electron noble gas format, or complete electronic configuration. Now electron configuration and valence shell is an idea. that valence electrons are very important for chemical reactions. Therefore, we need to know about valence electrons. Valence electrons are the outermost electron that goes to the highest number shell, electron that goes to the shell number with the large number. For example, for carbon, it is 2. You can go to periodic table and find out different elements have different valence shells. For example, lithium is 2s2. Valence shell is 2. Magnesium has 3s2. Valence shell is third shell. So for all these atoms, valence shell is the third shell because the electrons are filled in. For all these atoms, valence shell is the second shell or second period. Valence shell is the outermost incomplete shell. Normally, except noble gases, which have the maximum 8 electrons in the valence shell. Rest of the elements have lower than 8. An electron in a valence shell could be represented by a dot structure. For example, boron, right here. This number tells you 3A. I'm going to show them in a minute. 3A is the group in the periodic table. This has 3 valence shell electrons. 4A is a group in the periodic table. So it has 4 valence electrons. 5, 6, 7, 8. So for these 8 groups in the periodic table with group numbers with A, group label with A, directly number of valence electrons are the number in front of A. Okay, let me show you that quickly. I'm trying to go to periodic table. So do you see that 1A here, 2A here, 3A here, 4A, 5A, 6A, 7A, 8A? These are called main group elements. This with the A's are called main groups. Main group elements are extruded in transition metal and lanthanide and actinide. They are the important elements in the periodic table. Do you see where I got 1A, 3A, 2A, 3A, 4A, 5A, 6A, 7A, 8A? So you can go to the periodic table. You have the same notation in the periodic table. So I'm going. So these are the periods I was talking about, the tall periods in the periodic table. The A number in front of A is number of valence electrons. Therefore, when you write the boron, there are 3 valence electrons. You get them, put it like that. You put 1 and 2, like here. 4 is put in here for carbon. So we are going to talk about, when we talking about bonding, Lewis dot structure, right here. Lewis dot structure is that one. That one is a Lewis dot structure. How do you obtain them? You write down the atomic symbol and put the number of valence electron around it. We're going to talk about it more. So you understand how to look at the valence shell electrons for main group elements with 1A, 2A, 3A, up to 8A. Now let's look at the valence electrons in detail. Why valence electrons are important in the periodic table? Because the chemical properties of elements are decided by number of valence electron in the shell. How many bonds particular compound make depend on the number of valence shell electrons. Valence shell is the outermost shell with the highest value of N. For example, valence shell is here is 2, highest shell number. Therefore, valence shell is 2. For this is 3 here. Valence shell is 3. So valence shell is 3. The number of electrons, valence shell electrons are 2 here. You count only. This is 2 plus 7, 5 is 7. So from the electronic configuration, you can find out the valence shell electrons, highest number, shell number with atomic orbitals with higher number of shells, shell number. So you can get all of them added up. 3s2, 3p7, 5. You got 7. Now you learn most important thing in the chemistry. How to write an electronic configuration and find out how many valence shell electrons are there. Valence electrons are there from the electronic configuration and using the periodic table. Elements in the same group have similar electronic configuration. For example, alkali metal, lithium, potassium, sodium, potassium, rubidium, cesium, first group elements are called alkali metals. They have similar electronic configuration. Is S2, S1, S1. The alkali metal have S1. Alkaline earth metal have S2. But only the number in the valence shell is different. Valence shell number. They have the same number of valence shell electrons. The groups we describe in 8 groups, 1A through 2A, 3A, up to 8A, equals to the number of valence electrons. The number here is if you find the group in the periodic table, that number in front of A tells you how many valence electrons are there. Except helium, valence electrons are all for noble gases. Exception is helium. This is an exception for noble gases. Rest of the noble gases have 8, but the helium has only 2. Chemical properties of this is an exception, are all similar in a one group because their valence shell electron configuration is similar. So if you look at the valence shell electron configuration of elements, this is these 8 groups we talked about. The first one is first period, hydrogen. This is the alkali metal group right here. Lithium. All of them have 1 S1. How many valence electrons each one of them have? 1 valence electron. That's shown by here too. So alkali metal are here, the second group. 2s2. They have 2 valence electrons. They have similar chemical properties. Boron, aluminum, that's the third main group element. It's 2s2, 2p1. Only the difference between period is the shell number or the period number is 2 here, 3 here. So all these electronic configurations are same in each period, each group. So except helium. Helium is an anomaly here because 1s can have only one s orbital. There's only two. 2s, 2p. There are 6 of 2 and 6 electrons. So all of them after first period have valence shell. Main group has 2s2, 2p something. So valence electrons in main group elements we talked about in detail now. Now, I wanted to finish this up for today. I mean, these slides, because we have to start reviewing next class period. Let me do it quickly. The periodic properties of elements. We seen in the periodic table. It is constructed in a way based on electronic configuration, and they show periodic properties of physical and chemical properties, melting point, boiling point, and the chemical properties. With the understanding of electron configuration, we can explain the chemical properties in terms of electronic configuration in the periodic table. Periodic table works because in a particular group of elements, vertical column, they have the same electronic configuration in their outer valence shell. We look to periodic properties in slides to follow. We're going to look at atomic types and ionization. So we're going to explain how atomic size varies in the periodic table. If you look at carbon here and chlorine here, carbon is smaller radii. This is the diameter. This diameter is equal to this. Diameter is equal to this. That's the distance between. The diameter is this diameter of the circle. Half of it is the radius. Okay, radius of a chlorine atom is 99. How do you get 99? This divided by 2. How do I get 77? 1.54 divided by 77. So atomic radius can be calculated from solid structures by the distance between the centers. Radius is calculated. Why is chlorine has higher, large size? Chlorine is larger than the carbon. In chlorine, if you look at the electronic configuration, these are in 5. Last electron added is 3s, 3p5. This is 2p2. If you look at these sizes, 3p is larger here than 2p. Didn't we say that as the shell number increase 2 to p, the larger they become, therefore carbon has smaller size. Size of the 3p orbitals, 2p orbitals, and 3p orbitals. Therefore, orbitals make them atomic size larger. So you have to look at the valence shell of the atom and predict the size of the atom. General trend is going down a group increase, atomic size, radius increase. Going across the period, decreases, slight, large increase. Can you see these balls going down here? Much more variation in the size than here. So you are adding same shell number. Shell number is 2 here. So it's almost same size. But when you add in more neutrons going through these elements, the nuclear charge increase. Therefore, it shrinks the atomic size slightly. This is slightly. So going across the period, atomic size shrinks slightly. If someone asks you, fluorine here, nitrogen here, which atom is bigger, fluorine or nitrogen? Fluorine is bigger than nitrogen. Why is that? Going across the period, atomic size slightly shrink. The numbers speak for themselves. Going down a group, atomic number increases. So you can compare sizes easily within the same period. Definitely, what is found on the left side, right side, is smaller than what is found in the left side. For example, this is bigger than this one, like that. So you can use periodic table to predict the size of atoms through atomic radii. The last property we're going to talk about is ionization energy. Ionization energy is energy required to remove electron from an atom. This energy that is needed to be provided. So it tells you about reactivity of a substance. Higher the ionization energy, lower the reactivity. Lower the metals with, this is comparing metals. Metals lose electrons. Therefore, higher the ionization energy, more difficult to remove an electron from a metal. Therefore, it's less reactive. So periodic trend is shown here. Going across the period, hydrogen to helium, going across the period, going like that. Ionization energy increase. period is here. This is increase. This is transition metal. Transition metals are less increase here. It's kind of flat here. Then increase for main group elements. So therefore, going across the periodic table, ionization increase, ionization. Going down a group in the periodic table, ionization energy increase. This is the trend. So you can compare ionization energies for two elements here. This one, for example, nitrogen, carbon, which one has high ionization energy? Carbon has. Nitrogen has. Nitrogen greater than carbon. For lithium and potassium, which one is greater? Lithium is greater. Ionization energy decrease. I'm sorry. This is going this way. It goes up here, goes that way. Lithium is greater than sodium. Lithium, sodium. So on the top, it has more ionization in a group. So we have gone over atomic sizes and ionization energy. So we just completed chapter 2. We're going to review starting from next class period. Are you guys there?
Yes.
All right. We will see you on Thursday, right?
Yes, sir.
Yes.
Yes.
Do you have any questions?
No, sir.
No.
But that baby had a question. I heard him. He's learning from me, I guess. All right. See you next Thursday, all right? Take care.
Okay.